Hi, in this video, we're going to take a look at using the grammar of graphics for logistic regression diagnostic plots. All right, so in a previous video, I went through use base R to do the fundamental diagnostic plots for a logistic regression model. Now here, I don't want to use base R, I want to use the grammar of graphics. I'm going to use ggplot2. And now, if you've worked with ggplot, you know that it's powerful. It has a lot of oomph. You can get a lot done with it. You can control a lot of things. I feel like it is by far the best platform for data visualization right now. So because of that, I want to pull this in. I want to use this for my models when I'm checking out what's going on, when I'm presenting to stakeholders, to my boss, things like that. All right, now we're going to be using the package ggplot2. All right, so thank you, Hadley Wickham, by the way, for all the work that you've done. There was, for a short time, a ggplot1, I guess we'll say, but it didn't really work out as well as Hadley had hoped. So it basically got kicked to the curb, and ggplot2 was born. Now ggplot, the function is like the base of every ggplot plot. And so as we work through, we're going to be using that along the way. And how ggplot works, how the grammar of graphics works, is that it creates layers. And in the grammar of graphics, you can look at it as the goal is to have a mathematically consistent, mathematically describe. So from the point of view of a mathematician, how would you describe the mapping from data to image, and have it defined as a mathematician would define this, to have a consistent system and have like very powerful results. It's an amazing platform. All right, so what we want to do, I want to take the ggplot function in ggplot2 and apply that to my generalized linear models, specifically my logistic regression models. All right, so I'm going to take three approaches here. The first one is to use the GGLM package to get some geoms that behave like the standard grammar of graphics geoms, and I can just use those to pretty quickly get things done. Also, I'm going to very briefly go over ggfortify's autoplot function. This is a very nice function for producing quick, fast plots where I don't put a lot of work into it. It's fast, it's easy, but it's not very flexible. And also, in the middle, we're going to go under the hood, and we're going to do just a little bit of modifications to be able to invoke the full power of ggplot so that I can get exactly what I want and present the way that I want it to my stakeholders. So I'm not bound by the way that other people have set up their diagnostic plots. All right, so I'm going to go through, set my workspace, load my data, just like I always do. We're going to be using piping, so I'm going to use the Regression package, and I'm suppressing the number of digits printed, avoiding scientific notation, making sure my workspace is clear, and I'm going to be using the SA heart data set. So we're going to look at coronary heart disease, and the package is elementary statisticals learned. Now, this is an old package. To get this, I had to use DevTools install version to be able to get this. Anytime that you want to use an old version of an R package that is like in the archive of CRAN, you can usually use this function to get that onto your machine. Go to CRAN, find the version number, put it here. Here's CRAN for you, name of the package, boom, it will get on there. I find that this is a really good way when I start having problems with package version also. All right, and so I'm going to take my data. I'm going to convert one column that's binary to a dummy variables, and just to make my plots like more explicit. So when I present to my stakeholders, I want to have actual true labels on there. I don't want it to have zeros and ones for my target variable. I want to say explicitly coronary heart disease or no coronary heart disease explicitly as I go through my modeling. And so here, instead of having zeros and ones, I'm going to have the actual text. That way it'll make it easier for my stakeholders when I'm doing my presentation. And I'm going to slap on a constant of all ones just so that I have that on there for it'll come up later. All right, so now let's go ahead and go through. I'm going to build the model, and you'll notice that I'm using everything in the data frame except the target variable as a predictor. I'm not using, of course, I'm not going to use a target variable as a predictor, and I'm removing that constant because here in the implied formula, it will automatically assume I want a constant. If I put a -1 or a +0 in there, it will remove the constant there. And so one option I would have would be to have a plus here. If I had like a +0 and a plus constant, then it would not fit an intercept, but it would use the constant column to effectively get the same thing. But there is a difference in the calculation for intercepts for the formula, so it's better to let R just do it the natural way. And I'm going to go ahead and go through and just create a label just to spot to say, hey, if one of the influential measures are coming up in there, so what I'm going through here is this influential somewhere? So the influence measures function in R is going to create a bunch of columns that's checking to see, is it influential, yes or no? Is it influential, yes or no, all the way through, and it will give measurements. This will be a matrix of zeros and ones, indicating if by the measurement of the column, is that observation row, the observation by row, is that influential? And so if it comes up one or more times, I want it to be labeled. And so here I'm labeling it with its row number, so it's easy to find. And if it's not labeled, I'm just putting empty quotations, so that way I know which ones to look at, which ones not to. And for heart disease, I'll say that red is bad, green is good. And oh yeah, so here I'm just setting up what the colors are going to be on the color vector and loading ggplot2. Okay, so now we're going to go ahead and I'm going to list out all of the different models that are supported by GGLM. So it gives us a nice function of list model classes inside the package. And I'm just going to go ahead and sort them out. And so if we look through here, we can see that GLMs are available. So if I'm doing standard logistic regression, I can use, but you can also see I have a wide range of different models. So, I could be using a data frame, default model, factorial analysis, which ones are other big ones? Generalized least squares, linear models, k-means. So the lowest, these are ones I've used a lot. mclust for model clustering. mlogit, multinomial logistic regression, null model. That's one I've used a lot. Partition around the medoid. So Poisson modeling. These are, we've got, a good number or good range of models that we could use here, including, smoothing splines and survival analysis. All right, so let's do a simple example. So I'm going to go through, I'm just going to do the most basic simple example possible, just so that, I could just, do this real quick, grab it, get going. And we can see that we get the standard plots that I would get from base R, but they're using ggplot. And you'll notice I'm using, the default theme, I'm using, default settings on this. And, I mean, these look pretty good. I could look through this, get some information. Now, remember that when we look at our residuals, we don't have the same interpretation as we do when we do regular old linear regression. Linear regression, because the normality assumption of the residuals and all the other mathematics stuff that if you look at my linear models videos, you can dig into that. We don't have all of those assumptions. Like we don't have as much inferential oomph like as we would have if I was doing linear regression. But we know if it's bigger, something's more likely to be going on. So if I'm talking about residuals, bigger means that there's probably more of a problem. The residuals here, close to zero, like these are saying that, hey, the observed value and the model value are pretty close to each other. Up here, well, this one, well, that's kind of big, big and positive, and this is big and negative. All right, so it's the model is going, hey, it's going to be one way, but the actual value is the other way. And we don't have the normality assumption for our residual, so this plot doesn't make as much sense as it normally would. But we just know that bigger values are they're the ones that are more important for us to look at. And so these plots don't give us as much information as they would normally. Now, the leverage is still going to be applicable. Leverage is evaluated using the hat matrix. Leverage does not consider the target variable at all in any situation, any model. And so because of that, it's applicable to any model setting. And leverage is just a way for us to go, hey, is this really far away from the rest of the observations? If this is in terms of the predictor variable values, not considering the target variable, but if it's very far away, it's gonna be it's gonna like be able to pull the rest of the model towards it. And so these are the ones that I would be very interested in like double checking. And so as we do this, what I'm trying to do, I'm trying to see, does everything smell okay with my model? Does this look like reliable? Can I trust this? And are there any observations I need to double check? Maybe there was a mistake in the coding of the data. Maybe a sensor broke. Maybe there was some fraud going on with our customer. Our customer entered some bad information, and now like things don't make sense. I just want to double check things and see if there's any observations that should be maybe modified or removed from the data. All right, so the very most important plot for us for any modeling is going to be looking at our residuals versus the fitted values. That's going to be a huge one. Or another one would be the fitted values versus the observed. That will be a very those two plots are huge for us. But with logistic regression, I only have two for the observed values, two levels, so it's not as informative as this one. All right, and so what we're doing, we're going to be looking for plots that or looking for points that are sticking out that I want to double check. Maybe there's a mistake, maybe there's an error, there's something going on. All right, so we're trying to find extreme residuals, and these points may need to be omitted or modified. We're going to have two distinct curves because I'm doing logistic regression. I've got heart disease or no heart disease. That's going to form two different curves. They're going to have two different colors in a second. A perfect model would have all of the residuals close to zero. All right. And so here we can see what's going on with the model and the residuals. So green is no coronary heart disease. Red is that they have coronary heart disease. So this person here, this person has heart disease, but the model said that they weren't going to have heart disease. That's a problem. That is a problem that, as a diagnostic, it was missed. This patient could literally die off of, a misdiagnosis. Down here, the model said they have heart disease, but they don't. All right, so, this is now what would happen with these guys is that this is a situation where, maybe there was a misdiagnosis, right? It might be that the target variable is off. We don't actually know. But if we have 100% correct and accurate data, then there's a mistake here. And maybe there's a problem with these data points. Now, with the normal QQ plot, we do not have a normality assumption that we would have in linear regression. So we don't have, like, trying to follow the straight line is not part of this game. Basically, we're just looking for extremely different is is what we're doing. We're trying to identify extreme residuals, and these points may need to be omitted or modified. And we're going to have two distinct curves, and that's okay. All right, and so here we can just see that what's sticking out, what's sticking out. So, the ones over here and the ones over here, maybe I want to double check them. Don't put too much weight onto this plot. Now the residual histogram, once again, we're going to have two distinct like groups, and we're going to take a look at what's going on. And so what sticks out to me is that these look like they have different shapes to me. Like this looks like it's got a little bit of a right skew possibly. And so I'm wondering about this. And so like I feel like I've got two different shapes going on. And so, there may be some asymmetry in the diagnostic. It might be that maybe the diagnoses aren't getting, like, not all of the diagnoses are 100% correct, possibly. We don't know, but we just kind of see a different distribution. Neither one of these look normal to me, but that's not really that surprising. All right, now let's look at the scale location plot. Once again, we're trying to identify extreme residuals. And so here, the ones that are extreme are the ones that we're most interested in. So we can see that when it comes to extreme residuals, the ones with coronary heart disease are the ones that are sticking up the most. And so that's the main advantage of this plot. And so when we go through and we start like looking at things, it might be that these ones are ones that need some modification in our data set. All right, now let's look at the residual by leverage. This is used to identify influential cases. And so that may be good, that may be bad. We don't want anything to have too much influence on what's going on unless it's a super important observation. Like let's say I know that I've underrepresented a subpopulation, and so this one data point I want to have more influence, and we can use weights to do that. With But if I wanted to have everything have approximately equal influence on the model, I can use this plot to help find observations that have more influence on the model than on others. So observations with high leverage and high residuals are potential outliers. Such the presence of such points may warrant further investigation. Once again, we don't have the full power of linear regression, but we can accept the concept that large leverage means more influence than other points. And so here's the leverage, here's the standardized residual. And so what I'm doing, the points that are far to the right, high up, down low, are the ones that are most interesting to me. And so we can see that we've got some residuals here that are pretty big, but they don't have as much influence. Now, down here, this is decent amount of leverage, but the ones I'm most interested in are actually these over here, these four. Now let's look at Cook's distance and we're going to look at this by its row number, just to kind of try and find like where in the data set are the more influential ones. This is definitely an easier one to use when I have a very small data set. Cook's distance, what this does, this checks the coefficients from the default model, then delete one observation, refit the model, check to see how the coefficients change. If the coefficients changed a lot, we have a large Cook's distance, which is an indication that that observation has more influence. And so here, look at that, kind of surprising. So this is one with no coronary heart disease. There's more going on. And then we've got this over here. And so we can see that this is, probably less than 25. This is probably between 75 and 100, just eyeballing that. And so I at least have a direction to go when I start looking into my data. All right, so let's look at Cook's distance by leverage. So if it has high leverage, high Cook distance, we're going to be interested in. So this is popping up quite a bit. Check that out. That we already spotted that this one observation. So this is one that I would definitely want to go back and double check, make sure that everything is correct. All right, so now let's go under the hood and start customizing. Let's try to get the full power of ggplot. All right, so if I go through and I drop a generalized linear model into ggplot, here are all the slots I'm going to have. So here, this is the str function, the structure function. This is a really good way to see what's inside your objects in R. So here it's a list of 9, and so a list can hold anything, and they don't have to be structured. They don't have to be. They don't have to have a similarity between them. Lists can have anything in them, anywhere, any shape, any form. Along the way, it just has. But a list has to be like, there's a slot 1, slot 2, slot 3, slot 4. All right, so we have a data slot. We have a layers, scales, mapping, theme, coordinates, faucets, plot environment, and labels. And we control each of these when we call our ggplot. And one thing that's very nice is that I can modify these very easily by using like the ggplot plus, then add a function on there. And so here I have a p. I could take p plus geom bar, and it would add a bar plot to it. I could do p plus theme bw and change the theme from default to black and white theme, whatever I want to do. So here I've got my data inside there. Now the layers, I didn't do anything, didn't add any layers, so it's just an empty list. All right, scales, it's on the default setting. Once again, haven't done anything with the mappings. Theme is default. Coordinates is, default also. This is one that you'll spend a lot of time with if you're using spatial statistics, by the way. Faucet, I use faucets all the time for work. This one aspect of ggplot is why it's so powerful. This is why I professionally use this up, down, left, and right. This is where I have been able to get the most bang for my buck on my PowerPoint slides. And this aspect of ggplot has made my career, and I'm enjoying my life. And so everything else is on default. All right, so now let's take a look at the data. Now, this is something that's really nice in that if I just drop a GLM into ggplot, the data slot gives me that fitted value, the regular residual, the raw residual, the hat value. Now, the sigma for logistic regression is meaningless, so don't worry about it. The Cook's distance, so this is Cook's D, is how to read it. It's not Cook standardized, it's not Cook studentized. And then we have the standardized residual or studentized. It's where we take the difference between observed and modeled, then divide by the square root of the modeled probability of failure. And so we get these set up for us very nicely immediately with our row names and our data. I mean, everything is nice, easy peasy, lemon squeezy. I've got it very easy. Everything is in a nice compact space. So I can go through and start digging in. So the fitted values are the values from the predict function. The resids are from the residuals. Hat is from, it's just a hat matrix values, the diagonal of the hat matrix. The sigma is estimated standard deviation of the errors. I could also call that using the sigma function. Cook's distance comes from the Cook's distance function, and that's from deleting the observation, seeing how much the coefficients change. And here we have the standardized residuals from our standard. Okay, and so now I can go through and start invoking these pretty nicely. All right, so what I want to do, and I feel like this is a super important plot, I want to look and I want to compare my fitted values to the actual values that I would have. And so I can see like, all right, so this is whenever they did not have heart disease. I can see the range, and this is on the logit scale. I have not converted this to probabilities. I could easily, just do the math and convert it. But, we can see over here, everything's looking good. The ones over here are pretty far off. Now, for the fitted values when there's coronary heart disease, you can see that, a good portion of my box plot is on the wrong side. And so this is a problem. So that means that there's, like low modeled probability when the person actually had heart disease. Now here, let's look at the residuals. And so you can see, what's going on. Notice that, with the coronary heart disease, the residuals, going out past 2 are, but with no heart disease, they're not going past -2. And so, there's definitely an asymmetry on the errors. Now let's take a look at the hat values. So remember, the hat values do not consider the target variable. This is just looking at how far are the predicted variable values from the rest of the data. And so here, we can just see what's going on this. So we can see that, in turn, the box plot is showing that the ones with heart disease are having more influence than the observations with no heart disease. And this is something we didn't really pick. Like, you could definitely, the previous plots agreed with that statement, but here it's much clearer. It's easier to see. All right, now let's look at Cook's distance. All right, so that we can see that once again, the coronary heart disease observations have more influence on what's going on. And so, all right, well, so this is something just to be mindful of. Maybe, we might need to modify our model. Maybe we need to change some weights to get the things tuned the right way. All right, so now let's look at the standardized residuals. This will be very similar to what we saw before, but now look, we see things have split out because of the residuals in relation to 0, because close to 0 is good, away from 0 is bad. And you can see like this box, the median line is to the right of 0, right of 1, while this median line, the entire box, is on the inside of -1. And so we're definitely seeing bigger residuals with the coronary heart disease observations. All right, so now let's look at the standardized residuals and the hat values together. And so if I see, large standardized residuals, so extreme left, extreme right, and large hat values, then so like here, this corner and this corner are where I am the most interested in. All right, so that's how I can go under the hood and I can create any possible plot I could imagine off of my residuals using ggplot in a pretty easy manner. Now, what I want to do is use the autoplot function in ggfortify. This is a very quick and easy plot for us. That's why it's called autoplot. I mean, you can drop just about anything into this function and it's going to spit out a decent plot for you. Now, there's a catch. When I do this, I don't get the full power of ggplot. I don't get the full power of base R. This is a rather coarse and flexible system, but it's easy peasy lemon squeezy for us. So let's go ahead and use that. If you ever are unsure how to plot something, the auto plot function is a good one to try. And so here, I'm just going to go through and do 5 of the possible plots in base R. And, not much work, got things to spit out here that these two observations that we noticed before. That now something that this will always do, this will always label the three most extreme. And so if I only have 4 data points, it's going to label the three most extreme. If I have 1,000,000 data points, it's going to label the three most extreme. You know, if I have 1,000,000 data points, the three most extreme probably is not enough to capture all of the anomalies going on. If I have 4 data points, 3 is probably too many. So keep that in mind as you look through the labels. But you know, here, if I keep on seeing the same number over and over and over, that's an indication that I want to double check that observation. All right, so for your homework, build a logistic regression model and create diagnostic plots. Get creative, do things that you find interesting. Do the data science the way that your mind would find the most interpretable, the most interesting, the easiest to understand, and post it onto Canvas. Well, that's all I've got for you. Life is short. Do math.